in the space, and we have a fixed surface area. We want to find, okay, when it encloses the maximum volume. Okay, so therefore, and everyone knows probably, you know, in mathematics, and we know that only the ball, okay, maintain the maximum volume. So therefore, if we have a domain and with a surface area A and the volume is V, then this satisfies this A minus this N. This omega N is volume of the unit ball. Okay. So this inequality holds if only if the K is a ball. Okay. Then later on I will introduce with this. Okay. In the case of dimension 2, okay, among all plane domain with the fixed circumference L, then the disk of radial encloses the maximum area. That is, okay, we have this L squared minus 4 pi A is positive. The equality holds if and only if. And this includes the max area. Okay. For example, we have just to show the picture here. Okay. If we have a curve, okay, there's a curve. Simple curve. Simple curve, that means without a self joint. Okay. Therefore, we keep this as L. Okay. If this is D, okay, this outer length is L. Okay. If L is constant, okay, L is constant, okay, constant. We ask, in which case this D is get maximum area, enclosed maximum area. Okay, so of course, only case this one, okay, this one here, okay. This we have. This is L minus 2 pi, okay? This is the radial, okay? So actually this means, okay, we have the maximum, okay, all the area enclosed by this gamma, okay, this is D, okay, for this, okay, and, okay, this L is fixed. Okay, so this is okay. This is partial D, the boundary of this D. Okay, this is simple. Okay, okay. So this one, okay. Measure D. Okay, this is only when what's happened. Okay, this is one. This is L squared minus 4 pi, okay? This one. So this is isoparametric inequality, okay? And you just look at this one, okay? This is I just mentioned that this is L, but this picture is a little. This should be, you know, a little big, okay? Okay. So the isoparametric deficit, because this is positive, okay? So we define this as isoparametric deficit. So actually, this quantity just measures the deficit between a K and a disk of a radial. Okay? So if this quantity is big, so that means this is far away from a disk. Okay? During the 1920s, Donaldson proved a series of inequality of the form. Okay? Because this is positive, so maybe there's a quantity of B. This quantity is invariant of a geometric significance, has following basic. B is non-negative, and also B is vanish when K is a disk. Okay, B is 0, so this is 0. So this must be a disk because we have this one here. Okay, so and equality of this type is called the Bonus-Stein inequality. Okay. So many B's are found in the last century, and mathematicians are still working on those unknown invariant geometric significance. Okay. Whenever you found the B, okay, then you have a Bonus-Stein inequality. Okay. Over the past 100 years, and many mathematicians get some Bonus-Stein inequality. Okay. I want to point out, and this equality called the classical isoparametric inequality. Okay. There are many proofs in the past, but the first one, mathematically, proof, the non-proof is by Weierstrass, the use of variation method. Okay. So therefore, okay. And also another bonus and isoparametric inequality. Okay. So therefore, if this is a K, this black one is a K. Okay. And if this is a blue one is a disk, in disk, maximum in disk. Okay. The disk. And also the disk, circumdisk, smallest one. So therefore, this K is between this and this disk. Okay. So therefore, Bonus's isoparametric inequality says that this positive is pi squared minus RE. RE is the radius of circumsquare minus the inside one. Okay, this is a 1. This is a 1B we find. And you can see the meaning of that. Okay, if this B, if this equals 0, this equals 0 if and only if RE and I, so this must be, and or this equivalent to this one. So therefore, the K inside must be a disk. Okay? So the geometric meaning is obviously here. Okay. So Bonus-Stein inequality. Okay. And those previously, this Bonus proved this inequality. Bonus, then later on, okay, because it's since this R, if there's R between this RI and RE, then they have those inequality. Okay, so those inequalities are found in last 100 years. So many and people prove that the classical one. Okay. Okay. So therefore, the bonus inequality for domain in sphere on a hyperplane. Okay. Naturally, we want. Okay. Later we'll see. Okay. What's also bonus Stein inequality is also in a space. Okay. In a space, 3-dimensional and n-dimensional. But the basic one. Okay. What's the bonus Stein inequality for domain in x epsilon 2. This epsilon equals 0, that means in Euclidean plane. If the epsilon is positive, that's a projective plane. And epsilon is negative, that's a hyperbolic plane. So the Bonus-Stein inequality for the domain in plane and Euclidean plane for epsilon equals 0, the projective plane for epsilon positive, the hyperbolic plane for epsilon is negative. Of constant curvature, works of Klein and included myself and students. Those papers published in 2007. Okay, and the Klein have this one. Okay, so therefore this is they have. This is defined, well defined. Okay. And if epsilon equals 0, epsilon comes to 0. So therefore, this one is exactly just RE and RI. Okay. And then, later we have this one, and this one have something about this here. This shouldn't be here, but that's the work and done. We just list it here, okay? And also we get more, okay? All those type of inequality is generalized to the plane of the constant curvature, okay? Okay, so what's this? Those Sn epsilon, Tn epsilon is those, okay, here. So epsilon 0 is R, this is 1, okay. Okay, so we just the Bonason style inequality is isoparametric deficit, low bound, because greater than B. Okay, so one question is asked, okay, how bad this D is far from a disk, okay? So you close the disk, then the isoparametric deficit is small, very small, close to 0. So how far it could be? Someone said, okay, maybe like the case. If we take this drill like this, okay, like this one, okay, this is far away. So for this K, right, we also have this K. This K must be big. So how big? If there is a variable here, if there is a UK, okay, this UK cannot be infinite. We just hope you can find the B. What's the worst for the D? Far away from the disk. So that's the ask. But mathematicians are mainly interested in and focus on the low bound, BK, of the isoparametric deficit. There is another important and interesting question. Is there an invariant UK of geometric significance such that it is less than this, okay, bound above? Of course, we expect that this BK vanish when K is a disk. If K is a disk, this K must be 0, okay, it's sure. Okay, so the study of isoparametric deficit has a long history, okay, in geometry, and is still one of the main focuses in geometry and analysis. And recent paper published in Annals in 2007, and a professor from Stanford, and he get some Bonason's inequality for high dimensional. Okay. Unfortunately, we're not aware of any general upbound, okay, UK today, except for special case and something we unfortunately I have some work involved in this. Okay, but for the upbound, we have very strict condition. Assume that the boundary of K, this is K, boundary of K of convex domain has a continuous radius of curvature, and let this be the greatest, the smallest and the greatest one. This back to 1933. Botheimer found the upbound of this deficit up. Okay. So therefore, this one, the very restrict. They must be the over domain. That means cannot be any line segment on the boundary. Okay, so this is not just a convex and also, okay, this is like this one. Okay, this is the K. That's the strict convex, and this is the radial for the curvature radial, smallest one. This is the biggest one, largest one. So therefore, this must be large, very large. This rho m, this rho capital M minus m. So this is bounded by this. Okay, the formula is beautiful. So this bound is a very beautiful one. Okay, this is the one here. Okay, so this is here, and then in 1955, Pelagiel obtained improvement. Okay, this is pi. 4 minus pi. This is the one is much better than the one because that one is pi squared. Okay, so this is two-dimensional. Okay, then this is just 2010, and we have this upbound, and when K is a convex body in the two-dimensional Euclidean space or the plane, Euclidean plane, two-dimensional hyperbolic plane and projective plane. Then we assume that K is H convex. H convex, that means we don't have the line segment on the boundary. Therefore, we have this one too. Okay, when this epsilon equals 0, then was this back to this back to the Artemis one. This one, okay. This one. Okay, so because I was invited to AMS PDE workshop and held in University of Oklahoma. Okay. All the mathematicians from PDE, okay, they invited me to give a talk there. And I just wondered, I said, okay, why they invite me there? Because I'm the geometer, okay. Nothing to do with the PDE. And since, you know, they invited me, I have to find something, you know, related to the PDE. Okay, fortunately, then I just to search the paper. Okay, then that's just by chance. Then I find some the work is related. In two-dimensional is related to some flow. Okay, so that's the big surprise, you know, for me. And then we find, okay, I will and give some see here. Okay, so first of all, because we set some convex, okay, a set of points in Euclidean space is convex. If for all x, y in K and lambda, then this means the segment connecting x and y is still contained in K. Okay, so therefore you can see this one here. Okay, any x, any y here. So this segment is lambda x plus 1 minus lambda y. This segment is all in K. Okay. So if someone said, okay, this is one. This is non-convex because you see this 2 point here, you connect the 2 point. This is not in K. So this is not a convex. So this is convex here. Convex. Convex is that you can say, okay, the disk, the ball is convex, ellipsoid is convex, the simplex is convex. Okay? So this is convex, this is not convex. You can say, okay, this square is convex, right? It's convex. But if you delete 1 point, 2 point here, not convex. Because you connect it here, this point is not belong to there. Okay? So they're convex. So therefore you convex. So for the convex body in the last century, developed in last century, and and also now it's many people involved in it. Okay, the Minkowski sum and a scalar product of a convex sets K and L. If K and L two convex sets, we define, okay, K plus, this is a sum, L, this equal X plus Y. This X belongs to K, Y belongs to L. This is just the vector, you can add those two vectors together, okay? Then what's the scalar product? The scalar product is just lambda. Lambda is positive. Okay? Homosity or homosity of a convex set is a form of this. This just means a translation and dilation. What's a translation and dilation? Okay. Okay, if you are K here, okay, this is a K, right? This is a K. Dilation is just, okay, you this one, okay, this one, dilation, okay, or this is dilation, okay. Just expand, this is dilation, okay. If this is K, and this is lambda K, okay. This is another mu K, okay. Can be shrink, can be expand, this is dilation. Okay, a homosity is just a translation. What's a translation? If this K is here, okay, if this K here, then you have X here. This is X, so this is translation here. Okay, just this moved here, just a translation. So that means this is translation and a dilation. Okay, there's a dilation here. So therefore, if this one is L, therefore we can say that, okay, this L, if this L equal X, a translation plus a dilation, okay? Okay. So this is called so we call the L and the K are homostatic. Okay, homostatic. Okay. Okay. So a convex body, what's a convex body? A convex body is a compact convex set with non-empty interior. Okay, and someone said, okay, this assumption what's different? Because in a plane, in a Euclidean plane, right? Euclidean plane, okay. A line segment is a convex set, okay? Because any point the connecting is still in this one. But this is not a convex body because there are no interior, okay? Interior, that means they have a small interior. So this is a convex body, okay? Convex body with just like this, okay? This is a convex body. The line segment is a convex set, but not a convex body. Okay. So a convex body is defined. What's called the support function? The support function. A support function is okay. If this is a convex body, okay. What's a support function? Support function is like this. Okay. 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 Then you have the for any here, any point here, if you have the hyperplane, tangent plane, you can say the tangent plane. And what's this rho x? Rho x is distance. Okay, this is distance from the original to the tangent plane. Okay, so that's this is the support function. Okay. Okay. So in two-dimensional case, in a plane, dimensional case, a line in R2 can be expressed by this. Okay. any line, you can see the line here is okay. So if this is a plane, this is a plane in R2, okay, in R2. Therefore, this is a line. This is G. We call this G, and this is P. This is phi. This line is uniquely defined by the distance. This is P, okay? From origin to here, this distance, okay? And the angle by this one, okay? Phi. Then, okay? So, when the phi and the P is given, so therefore this is given. The only sense if this line passes through the origin, okay, so that's a P is 0, so that's semantic, so that's defined by phi. Okay? So in two-dimensional case, we have the function because this is just a support function. Two-dimensional case, okay, phi is 0 and 2 pi, and okay, it's nothing A, B here. Okay, so P. Okay, sorry, it's a P. It's P. It's from 0 to infinity. I'm sorry, there's some miss here. So the convex domain, the K, is uniquely determined by P. Okay. What does it mean? Okay, if P are given, and then we have the P is a P phi. Okay. Then we have the envelope for this. So therefore, we have the convex set, the convex boundary. So any boundary here is determined by X, this one, okay? Okay. Then we can say what's the Wolf length? Oh, this is this is something with the topologist, and they call the Wolf curvature and the Wolf length and the Wolf flow, and that's the beginning. They try to prove the Poincaré's conjecture. Then they just to see if in two-dimensional. Then they just try how use the two-dimensional to three-dimensional to high-dimensional. Okay, so that's we find something is interesting for us to interest. Okay, we have letter 2k. We have a two convex domain with a support function P. This P is this P. Okay, and we consider the area of a convex set. We just said because this K is K, and this is T. This T is a real value, and with Ki, because Ki, Kj are convex, and the Tki that is just a dilation. So we have this is a Minkowski scalar product, and this convex set. This also convex set. Two convex set. That's a Minkowski sum. Okay, that's what we define. It's well defined. Then we consider the area for this convex set. So this area convex set is something related to T. Okay, so that is the AI T square plus this is a total. That means this is 1. This is called the Wolf length. And this is AJ, that's the area of AI AJ. And then we have a Wolf curvature, okay? And this is a Wolf radial of curvature, that's just this is reciprocal, okay, with this one, okay. Okay, we'll look at what's this actually, okay? What's the meaning of, okay, first we have Ki, okay? Then we have T, a translation to here. It's a boundary here. Okay. This is then we have Ki. This is Tki. Therefore, this is Tki. Then we have the dilation. Therefore, Ki plus this dilation, we just move this. Try to whip it around. Okay. So therefore, picture like this. Okay. Then we compute the area of this. So the figure K plus T. Okay, this looks at something like this is just something like the flow. Okay, this is like the flow. Okay, one special case when Ki is a unit disk. The unit disk, then this this exactly is a Wolff-Steiner. Okay, so this Wolff flow associated with the TK. This is Wolff flow. Okay. Okay, therefore, special case, when this Ki equal unit disk, then all this we call Kj plus Tb. This is, we call this one is the parallel convex set. Because this is a convex set, the parallel, okay? You everything distance, okay, parallel convex set. Okay, so when this flow, constant flow, okay? Constant flow, that's the T. So this says T, this says T. Okay. But if this is not, because this is around the normal, okay? Because if this is not the special case is a unit disk. If not a unit disk, and we should have more information, okay? Okay, so therefore, at a time, okay. Okay, then we have the property, okay? Now this one, this L, Ij is symmetric. This is defined, well defined here, okay? This is well defined because the Pi is given. This boundary is also given. So this is a quantity we can compute. Then we can have, okay, now we have this is a symmetric. And also the monotonic, okay? What is this monotonic? So if there is another KL such that this is smaller than this one or contain that one, therefore we have this. This means monotonic. In special case, when Ki is a disk of radius R, so therefore this is just known. Okay, this is a simple one. Also the green and also a Steiner polynomial, Wolff flow, and some new isoparametric inequality for convex plane curve. Okay, so this is all this, and all this concept is in the paper of in 1999. Okay, but those property they didn't get this property. Okay. And this property, if according to what they define, that it's difficult to prove. But for us, for me, okay, in a geometric way, in a special case, we can prove this. Okay, then notice that Wolff length is symmetric, so the equation is called the Wolff-Steiner polynomial. The Wolff-Steiner polynomial Kj. We want to get the area, okay? We want to get the set of this area, okay? So we get this area, okay? This is K plus this translation. Translation, we can give this up, okay? So therefore, we want to compute of this area, okay? Include the inside, okay? To get the area of this one. It's called the Wolff-Steiner polynomial of degree 2. And if Ki is a unit disk, then this is reduced to the Steiner polynomial. Steiner polynomial is known. It's in geometry, integral geometry. Therefore, okay, integral geometry, the Wolff length is this just called the mixed the mixed area. So therefore, we have a Minkowski inequality. Minkowski inequality is aij squared minus aij, the positive. So therefore, okay, so therefore the with equality sign holds if only if Ki and Kj are homosthetic. Homosthetic, that means a translation and a dilation. Okay. So equivalent to this Wolf isoparametric inequality. So the Minkowski inequality guarantees that Wolf's line polynomial and in algebraic geometry. Okay, so we invested this special case in two-dimensional. This is a polynomial about t. Okay, this is about t. Okay, therefore, and guarantee the Wolf's line polynomial have two roots. Okay, we want to find the roots for this one. If this have a root, have two roots. So therefore, what we call the symmetric mixed isohomosthetic deficit Ki and Kj is defined as this. Okay, why we is called the one? Okay, and since in the beginning, okay, we said that we want to compare and two domain. This is a K domain, and then disk. Okay, this is a disk. This disk we have L over 2 pi, the radius of this one. Okay. Therefore, we have delta K. Okay, this equal L squared minus 4 pi A. This is greater than 0. Okay. We just compare K with a disk of the circumference. Okay. So here we just if we give any K, okay? If given, this is like the Ki, this is like the Kj, okay? 2K. We just if we give any K, this is the Ki, this can be the Kj. We just compare, directly compare them, okay? This we just compare with the disk. We compare this one, therefore, we have, okay, what's this is defined Aij and minus 1. Okay, so this is Aij is the mixed area of Ki and Kj. Okay, this is 2K. So therefore, we will have this, because this is positive. So this is Minkowski inequality. Equal 0. This equals 0. So therefore, we call this one, okay, sigma 2. That means dimension 2. Ki, Kj. This equal a, okay, Ij squared minus Aij. This is positive. So equality holds. This equality holds if those Ki and Kj are homosthetic. That means a translation and a dilation. Okay. Okay. So therefore, if you choose one as a disk, then this is just back to this one. Okay. So that's we just direct compare. So we call this a Wolf isoparametric deficit towards the Wolf flow. Is this one. Wolf flow is the Kj, it's the norm here. Okay, forget this one here. Then you can see that So how can we get this one? We try to get some inequality for the water flow. Okay, we just compare this one here. Okay, if this is the Ki, we have translation here. Then we have dilation. We have dilation. Okay, we let this Tm such that this dilation is contained in this Kj, in this K. Okay, so this Tm is a maximum dilation. Okay, expand, but inside. Okay, so this is a T, and what's that is a T capital M. T capital dilation is big. Then we just shrink, just contained. So this is the minimum one, minimum T. Okay, so also this is by the flow people, the PDE people, they call the Wolf radius, Wolf in radius. We call this Ti. This is a Wolf out radius. Okay, so therefore this one, if this is a unique disk, then this is just the inscribed disk, the outer, the circumscribed disk. This is nothing. This is natural. So therefore, then we get quite of those inequalities. Okay, if T is between those, T is here, then we have this inequality. Okay. Each inequality holds as an equality if only if Ki and Kj are homostic. It's homostic.
So you mean one inequality holds?
Yeah, each one. This holds. This holds must be yeah.
All
yeah. All. Okay. All inequalities. Okay. Yeah. Okay.
At the same time.
At the same time, yes. Yeah. If this holds, okay, that's must homostic. Okay. Very special case. Very special case. If you take the Ki is a unique disk, so everything this is just what we have the Bonason style inequalities. Okay. So this is a natural generation for the Bonason inequality. Okay, and therefore we get this one. This one is also is proved, and this is the one is the conject. They conject in the flow in two flow, and the people. But we proved, I don't know, because I searched, I couldn't find. Maybe someone proved, but I don't know. So I just put the question mark here. Okay, so this is the one we have. Therefore, we also have this. Okay, so this is those is the flow work, and also the special case one. Okay, this Tm capital M, Tm. Those is Bonason. Was Bonason, Blaschke, Flanders, and the equality holds if only if Ki and Kj are homostic. Okay, this equality in the sense of a convex set is due to Bonason. Later, an elementary and simpler proof has been given by Blaschke and Flanders. So another elementary proof via integral geometry. Integral geometric method, sorry, miss it here, is given. Okay. Okay. We also, Yue is one of my students. Okay. We just wish we get more. This one, this is better, improvement. Okay. See this one here. This is by Bonason, Blaschke, Flanders. Okay. This is the best we have before. Then we find, okay, we can have something more here. So this is improvement of this one. Okay, so we have this here, we have here, and we also have this, and each equality holds as an equality if and only if there is x that means Ki and Kj are homostatic. Okay. So therefore, also, and most very surprising, okay, surprise, and we get a surprise. We also can get the deficit, the up. We get up bound, This is 3 up bound, and this is I believe those are new. Okay, new. Okay, we also have those equality here. Okay, so what? And back to what? Okay, since a few minutes.
No, 20 minutes.
Okay, I take just a few minutes because we started earlier. Okay, okay, all right.
How do you find the translation
10
point?
minutes.
Huh?
How do you find the translation point X?
Translation.
Yeah, translation and dilation.
Okay. Actually, we are not exactly find from the picture here. We use the method. We just estimate. We do not actually define the translation. We just if there is a translation, then we estimate some formula. That's the integral geometry. Yeah, yeah. Okay. So therefore, actually, we just estimated this one. We're trying to find if there's a translation such that this included there. Okay, so here we have missed something here. Okay, here's a crucial. Everything is crucial at this one. Okay, it's crucial. Okay, if this is a very important one. Okay, everything is based on this formula. Okay. In integral geometry, we just trying to find if we give two domain, okay, two domain. One is K, okay, this is K, this is Ki, okay, this is Kj, okay, this is Kj, okay. We want to see if there is a translation such that this can move inside of Kj. Okay. If this exists a translation T such that this T, K, I contained in Kj or this T, Ki, because we don't know, Ki may be the big, so also and contain the Kj, okay? Yeah. In other words, okay, a translation and a dilation. Okay, the dilation, maybe the dilation, okay? So therefore, we can add this here, a dilation. This is a dilation, okay? We move the dilation, okay? For example, this is just a translation, okay? Okay, if we have one here, okay, this is a T, okay? This is a T, right? T. Then this is a TK, okay? Okay, a dilation. Dilation maybe this one, okay? This one, dilation. This is a T, capital K. Okay. This is inside. Okay. So therefore we want to find those dt. Okay. That's T is well defined. It's in integral geometry. That is a half measure for the group. Okay, rotational group, registered motion, and the translation is well defined. Okay, so we trying to find. Okay, we're trying to find the mu. Okay, the mu is a measure for those t, such that this t, the tk, I contained in Kj or this T, Tki, okay, Kj, okay, this one. Okay. Then this one should at least those must intersect. Okay, we must find those T. Maybe T is many. We find those T. Okay, this T such that this T, Tki, and Tj must intersect. Okay, and also, if we want this contained inside or contained, the boundary cannot be touched. Okay, so we must minus those T such that the boundary of this T, Tk, and this boundary Kj not empty. Okay? Okay. So this formula is okay. This formula is Blaschke. Okay. This is a formula. This Poincaré. Poincaré in 1919. Okay. So therefore, okay. So therefore, we use these two formula, then we get. That's what we get. Okay, use the formula, and once we get this one, then everything looks better. Okay, because we see that what's the Tm? What's the Tm? Okay, what's the Tm? Okay, Tm is outside, it's chart. This small Tm is inside. Okay, so therefore, when T between Tm less than Tm and this cannot be contain each other, right? Because it's between here. So therefore, this mu equals 0. So therefore we get this is less than 0 when T in here. So that's the one. This is the one we have. Okay. This is immediately the theorem. We get this is a positive. And this is same, we don't know where we'll get this one, we don't know. Okay. So therefore, okay. So therefore, that's the theorem we have. The Bohnsen symmetric mixed homoscale equality. Okay. And the Bohnsen-Wolff homoscale equality. This inequality, and they should find for the below people. This is the formula I proved, and therefore you can see. That's a picture like this one. Okay, just a quadratic. This is a quadratic the curve. Okay, this is not equal 0. This should be this just without 0. Okay, this is T. Okay, so therefore, because it is sigma, we have two roots. The two roots, we get minimum value, minimum for this one for K. So therefore this. So everything we get called the both Bohnsen and polynomial. So therefore we get this one. Okay. So the Bohnsen, Blaschke, Flander, we don't know who's else. Okay. Okay, this is the one. Okay. Okay, there's those. And this is the one. Okay, so I think I just stop here today. Thank you.
Very interesting talk.
Any